All right, electricity. Biggest thing we have to know before we really understand electricity is we have to get down into the smallest thing. I notice we got some people without their name cards today. I guess make it hard for me to remember who everybody's name is. We have an Adam here. Adam? Oh, good. I'm glad Adam's not here. You can never trust an atom. They make up everything. Right? They make up everything. Everything is made up of atoms. And atoms have a nucleus. I don't know how to spell nucleus, but it's nucleus. And nucleus is made of protons and neutrons. Those are jimmies. All right, protons have a positive charge. And neutrons have a neutral charge. Or no charge at all. That's the nucleus of an atom. And atoms together make up molecules, and molecules make up everything else that we have going on. Even the air, made up of atoms. The tables, the floors, the carpet, everything, us, we're all made of atoms. Everything. Atoms make up everything. So it has a nucleus in the center, protons and neutrons, and then also orbiting the outside of this atom, we have electrons. And they're different little ranges on the outside, but they're orbiting all the time, in motion, orbiting the nucleus, all the time in orbit, moving, constantly moving. Everything's in motion. This table is in motion. Those electrons are moving around. Now, different atoms have different number of electrons on them. Some have more electrons, some have less. There's a science behind how many rings have how many electrons on them, and blah, 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 blah. What we're really concerned about is the valence electron, or this one electron over here by itself on the very outside edge. That one we can kind of manipulate. We can kind of mess with it. We can play with it, right? We have some fun with that one. So all of these molecules, everything's made of molecules, so all of these atoms are all here side by side next to each other. What I can do with this atom here is take an electron, and with this electron, I can take this electron and hit this electron. But now there's too many electrons on this one, so it's going to knock this electron off and knock an electron off to the next one. And that's going to knock an electron off to the next one, and into the next one, into the next one. That is electricity. It's not really a thing. It's not a substance. It's not something we can actually buy or store. It's just the moving these electrons off from one to the other. So what I have here, a little demonstration for you. Completely unscientific demonstration. I'm going to volunteer. Thanks. Yeah. All right, so I need you to hold this. We're going to put, these are going to represent electrons, these little ping pong electrons. Now, I can't put the nucleus in here and orbit them very easily, so it doesn't really work well for a demonstration, but this works pretty good. These ping pong balls represent just simply electrons, so I have to, I'm representing this being this pipe being a piece of copper. And these being electrons orbiting, those three electrons, the valence electrons. All right, so there we go. Electrons are there, right? So here we go. I take an electron, and I push the electron on this side. Oh, what happened? Now, did that electron I pushed this side come out over here? No. One hit the next, one hit the next, and hit the next. Let me show you again. Oh, look at that. Show you again. Look at that, right?
Somebody catch these balls, man.
Right, this is electricity right here. Every time I put an electron in one side, electrons come out the other side. Right? Electricity. This is electricity in its simplest form. Does that make sense? These are moving in one direction. One direction. We call this direct current because it's going in one direction. DC current. Any questions? Direct current. It's in one direction. Without the rhythm. Direct current, one direction. This is what we use typically in batteries. Battery. So let's use a car battery. What terminals do you have on a car battery? Positive, negative. So let's put, we got positive here, we got negative here. All right, which way is the electrons flowing on a car battery? Everybody agree? Let's go back to an atom and what it's made of. What's the nucleus made of? Protons and neutrons. Right? The outside is the electrons. So in the battery, my negative side means it has a net negative charge, which means there are more electrons on this side. There's the same number of atoms in each side of it. The same number of atoms, although this one has more electrons. We squeezed a whole lot of extra electrons over here on this side. This side has less electrons. It is short electrons, but it's so since there are less electrons, it has a positive charge because there's mainly protons in there. Does that make sense? There's still protons here, but there's way more negative electrons. Here, we have a few electrons, but it has a positive charge. There's not enough electrons. So, in Earth, it wants a balance. So, these negative electrons are going to want to go in. Here to this side. So, they're going to want to flow over here to the positive side. So, electricity, and all DC, and your car batteries, and everything else, the electrons are actually flowing from negative to positive. The chassis ground that we all think of as ground is not really ground, it's chassis, right? That's actually, you're energizing your whole entire car, and those electrons are wanting to flow to the positive side. What we call the red wire, the positive side, is really where they're trying to get back home to. Kind of mess with your mind, doesn't it? But it doesn't matter which way I stop the flow. If I stop the flow on this side or I stop the flow on this side, if you stop the flow, you stop the flow, right? So, it doesn't really matter which one's which because as long as we stop the flow, we shut everything off. But electrons do flow from the negative to the positive because we can't change. I can't move the protons of that nucleus. I can't move that atom, but I can move the electrons orbiting it. Pretty cool, huh? All right, to have a circuit, before we get there, that's direct current. It's flowing in one direction. But there's also AC, which is alternating current. Alternating is flowing in either direction. Right? So let's talk a little bit about alternating current. Here's alternating current. Ready? Pushes this way, pushes back this way. Pushes this way, pushes this way, 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 this way. Are the electrons moving?
Yes.
Yes. Are they going in only one direction?
No.
No. They're changing direction, right? Positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. See how they're switching back and forth? Are the electrons moving? Yes, that movement of electrons is electricity. It doesn't have to be in one direction, does it? This is alternating current, AC. Alternating current. I'm alternating which way I'm pushing, right? That's alternating current. In the plug outlet here, we have alternating currents, changing directions from positive to negative. It's changing directions. This is everything we have with plug outlets. Alternating current goes longer distance. Thank you, Tesla for this and Edison for this. So far, so good? Alternating current. Now, how fast does it change between positive and negative here in the U.S.? Anybody know? 60 times per second, or cycles, or also known as Hz, hertz. Put those into a locker and make a movie. Alternating current changes direction 60 times a second, and really quickly we'll introduce a sine wave to you. Sine wave, you have a 0 point. Electricity is going to go negative, positive, negative, positive, positive, negative, negative, positive. Here's the 0 points where it's changing. So it's positive voltage, negative voltage, flowing one way, back the other, flowing one way, back the other, all the time. Changing direction 60 times a second. These lights up here, are these lights on? Everybody agree? No, they're not. They're flashing 60 times a second. Actually, it's 120. Anyways, flashing 60 times a second. On, off, on, off, on, off, on, off. They're pulsating. Yeah, don't look directly at it. These spots. But it's pulsating between when it's changing. Now, a DC light bulb, it stays on all the time. But an alternating current, it's actually flashing. It's flashing so fast, you can't see it. It's flashing so fast, you can't see it. So we perceive it as being always on. Still the same result. Doesn't matter if it's flashing, does it? Still they have plenty of light for us. But that's called hertz or cycles. We're only seeing so many of these flashes, so we see it as always being on. Have you ever had anything ran by a generator? The generator starts running out of juice. As its cycles start slowing down, sometimes you can see some of the pulsations. You ever had a camcorder recorded something on TV? You saw the lines going through it? You're recording the pulsations of when it runs the new lines to the TV. You're seeing a certain amount of that pulse. Let me show you another example of cycles per second. Reboot. Okay, where's that? Yeah, right. Imagine that. You got the lights for me, please? You got that. What's the catch? Alright, so here's a little video to give you an example of what's happening. So what's happening is cycles per second. A camera, this camcorder is recording. It's in other words, it's taking pictures. It's flashing a picture, so many pictures every second. And as it flashes these pictures and everything, all the movies we watch is really just a series of pictures flying by really, really fast. And we see it as motion. So the camera is taking individual pictures so many times a second. This bird flaps his wings in a sine wave, positive, negative, so many times a second. Alternating current. His wings are alternating, positive, negative, so many times a second. So what's happening is he's actually flapping his wings at the same exact rate that the camera is taking those pictures. So the camera's not seeing it. Snap, the camera takes his picture, not seeing it. Camera takes his picture, not seeing it. Camera takes his picture. So as the bird's moving around, it's like, hey, it looks like this, right? But in reality, he's really flying around. That's an example of hertz, or cycles per second. Make sense? So far, so good? All right. Hertz, cycles per second. That's where it comes. Best example of it that I've done. We can go into a lot of detail about electrical theory. We can spend the rest of your life learning about electricity, electrical theory. One of the things I love to teach, what I'm trying to do is teach you guys just enough so you can do air conditioning electricity. So when we wire, we're going to wire as if it was DC. Although it's alternating current, we're going to wire as if it was DC. So if we're going to wire something, we must have three things to have what we call a circuit. How do you spell circuit? C-I-R-C-U-I-T. Circuit. We must have three things. We must have a source. We must have a path. And we must have a load. We must have a source, path, and load to have an electrical circuit. So here, if I have a battery, this would be my source. And if I had a light bulb, the light bulb would be my load. Or we also can call this work. What it's doing for us. We want it to do something for us. So I have a source, we have a load, but we must also give it a path. So the wires and the switches are our path. Does that make sense? Source, path, and a load. So we're going to have our source, in this case being a battery, our load, in this case being a light bulb, and our path is our wire and our switch. So if this switch is open, do I have a path? I don't. The switch is open. There's no place for it to go. But once I close the switch, I connect the path, right? So once I connect the path, now I have a source, I have a path, and I have a load. We have lights. I also really enjoy putting alternating current and direct current together at the same time, because then we're back in black. DC, okay? Anyways, so we must have a source, a path, and a load for anything we do with electricity. A source, a path, and a load. Source, path, and a load. Source, path, and load. So far, so good? Source, path, and a load. We have the light bulbs. That's our load. The wire's running, and also the switch is our path. And then our breaker panel, our meter, the big wires there, the Hoover Dam, all of those are considered our source. And if I break my path, we no longer have a circuit, right? And if I close my switch, then we complete the path and have the lights on. So far, so good? It's a deep concept. So let's, we got to get through the theory before we can get to actually doing. Most important part of electricity is going to be this. E over I and R. But it's not that simple, because nothing in HVAC is that simple, is it? Yeah, it's not. E is known as electromotive force. We can put electrical force. Electrical force. It's also known as electromotive push. Also known as electromotive pressure. Pressure. It's the push. It's the force. It's the pressure. And your faucets, like the faucets here in the bathroom, even though the faucet's closed off, is there still pressure behind it? Yes. Now, if I open the faucets and let the water flow, there's still pressure behind it. Yes. So can you have pressure whether there's flow or not? Yes. It's also known as potential difference. Potential difference. The potential for there to be flow. So if I wanted to check the water pressure of a pipe, I have to have a hole into the pipe. So I'm checking the pressure from inside the pipe compared to the pressure outside the pipe. Does that make sense? It's like our gauges are checking pressure from inside versus outside. If I wanted to have the Hoover Dam, and I took a scale and I dropped the scale into the bottom of the lake right there and let it sink to the bottom, is it going to give me the weight of the water? No, because there's no potential difference. The water on the inside, the water on the outside of the scale is equal. There's the same amount of water on each side. It's not going to give you any reading. You'd have to take it and put it into a container and put that container on the scale. Does that make sense? So potential difference between two different points. This is also known as volts. It's also known as volts. So this guy came up with this, and he used the letter E for electrical pressure, electromotive force. And then after he dies, they want to like, hey, you know, that's a really cool thing this guy came up with. Let's honor him, and let's call it after his name. And his name was Alessandro Volta. Alessandro Volta. So they started calling it, I'll just call it volts. How about that? So they started calling it volts after Alessandro Volta. But it's really E for electrical pressure, electromotive force, potential difference. Sound good, right? And then we have the next letter. Oh, so where our source is, this is the source of our voltage. That's where our source is. It's going to be the source of our pressure, electrical pressure. So right here at this plug outlet, there is voltage right here. Doesn't mean there's a flow. There's potential for there being a flow, but there's no flow. There's no path. There's no load for it to go through. But the pressure's there. Alternating current is changing direction 60 times a second. There's pressure here, there's pressure here, there's pressure here, there's pressure here, constantly, but there's nowhere for it to go. There's a potential difference between the 2 points, and if I hook a meter up to it, here's our meter, turn my meter over here to V for Alessandro Volta, and I put the meter leads in one side, and I put the meter lead in the other side, it gives a reading. What does that say? The potential difference between these two plugs is 123 volts. The electromagnetic force, the electrical pressure, the electromotive force between these 2 points is 124 volts. Now the voltage is changing between this side and this side, but it's changing so fast, whether it's positive and negative this way or positive and negative this way, the difference between those two, 120 volts. The pressure between those 2 points. Let's check and see what the pressure would be. Hold on to it. You have to lean forward. Sorry. I'm going to put both leads in the same exact side. What is that going to show us? No? What's the voltage? 0. Let's put both of them on the other side. 0. It's showing us 0 because there's no potential difference between where I'm using my leads. There's no potential difference. I need them in 2 different locations to have a potential difference. If they're both on the same side, there's no pressure. There's no potential difference. I'm putting my scale, so to speak, completely in both sides of the water. There's no pressure reading on it. You have to have it across 2 different points. Does that make sense? So it's potential difference. That's what this meter's reading. Anytime we're reading with voltage, what we want to do is use the leads of our meter. These wires are what we call leads. So we're going to use voltage with the leads of the meter. I got friends, and they're always in sales, and they're always looking for these. And I don't know why. I don't know what they need these for, but they're always calling around looking for these. They're always looking for leads. I don't know. All right, so the next one came from the pirates, right? Arr! It's going to be a long night of these. R. So this one, the R stands for resistance. they're also French pirates. So the resistance. Resistance to electron flow. The resistance to electron flow. R. So R stands for the resistance to electron flow. Loads are going to have, our loads are going to have resistance. Our loads are going to have some kind of resistance because it's slowing down the flows. It's going to do work. So resistance to electron flow. Now, the pirate that came up with this, he was a friend of everybody, right? He was everybody's ohms. Right? If I remember his name was I can't remember his name. Something. Anyways, he was Ohms. Everybody, the pirates were like, "Arr! What's up, Ohms?" Right? And so he wasn't a very lucky man. So they used the omega symbol, and the omega symbol was an upside down, unlucky horseshoe. Now, anytime some of you guys haven't grown up on a ranch, so any of the ranch people know that if you have a horseshoe, you always put the horseshoe like this. You always put the horseshoe like this because you need to hold the luck in. It's a lucky horseshoe. You got to hold the luck in. And if you turn the horseshoe the other way and only use one nail to hold the horseshoe, then it ends up like this, and the luck falls out. So you cannot do that on the ranch. So this is called the omega symbol, and on the ranch we call it the unlucky horseshoe because all the luck fell out. It's upside down. You would think I'm joking, but that's just God. That's like a real thing on the ranch. So it's the omega symbol. It says the omega and ohms like close together, like, hey, omega. Right? That all ties together. It's the resistance to electron flow. We can use the meter and we can actually determine what the resistance something has. All these loads have some kind of resistance to them. You can't really stop it; it's futile, but you have resistance there. And also on that same French ship, they also had the eyes, right? And the pirates voted on what letter to use, and the eyes had it. They also, their mateys had it as well. Aye, matey. They had the patch on it, so they had the one eye, so they wouldn't forget it. So the I stand for speed of electron flow. The speed of electron flow. How fast does electrons flow? The speed of electron flow is also known as current. Current. Anybody ever been in a river that had a current? Right? The stronger the current, the faster it flowed. You ever been in an ocean, you had a rip current? That was a very fast flow that ripped you out to the sea. Current is also speed of electron flow. And the guy that invented that was, my phone's recording, I can't pull up the name. It's a double first name, Ampere. He's a French guy, something Ampere. Can't remember the name of it. Anyway, something Ampere. And so we simply, to honor him, call it amps. Or some people still call it Ampere. So, and we really use the letter A for amps, V for volts, and the omega symbol for ohms. But it's still correct to use E for volts, R for resistance for ohms, I for amps. So they used it amps after something Ampere. He was French. So far, so good? All right, so we use the letter E for electromotive pressure. We use R for resistance electron flow. Why do we use the letter I? But what happened was with this Ampere guy, he was out with the pirates there, and they had gone onto this really cool island to bury their treasure. And so while he was waiting out there, he started doing some electrical experiments, and they were camping while they did this. And while they were camping, he thought, hey, you know what? The faster these electrons flow, the more current there is, the more intense this is. And since we're intense anyways, because they're camping, he called it I for intensity. So they use the letter I for intensity. You don't really have to know the letter I stands for intensity because it doesn't really help you with anything other than the fact that some people want to know why the letter I. And that's because they voted on it. They all agreed, hey, let's vote. How about intensity? I, and the ayes had it, right? So it's intensity, but really what you know is speed of electron flow, current, amps, ampere, all of that is with electricity. Okay? So I have my source, which is my voltage. I have my resistance, which is my load, and my path, my wires, and it makes all three of these happen together. All three of these together is electricity. This is electricity. Electricity, if somebody asks you, this is also called Ohm's law. Ohm's law is E over I and R. That's Ohm's law. Some people put that in a triangle, some people put that in a circle, but this is Ohm's law. So we said, hey, on an interview, sir, what's Ohm's law?
EIR?
E over I and R. That's what you say. It's the easiest way to give that answer. Now it's going to be an interview, too. It's going to be very scary. They're going to be staring at you. There's also a dog who's pulling in his pants like while he's doing this. All right, E over I and R. This is electricity. These three things, the trifecta, you have to have all three of these to have electricity. What happens if I take out resistance and I have simply a source and a path, but I have no load? We end up with what we call a short. A short circuit. Electricity flows too fast. It's going to burn something up. Okay? So far, so good? Great. So now what we're going to do is a little experiment to help tie this together. What time is it, by the way?